Dijkstra's algorithm. Dijkstra's algorithm is a greedy algorithm for finding the shortest path from a single source vertex to all other vertices in a weighted graph. This comes with a condition. The condition is your graph should not be having any negative weight edges. So if your graph is not having any negative weight edges, then you can use Dijkstra's algorithm to find the shortest path from a single source vertex to all other vertices. So why is it called as Dijkstra's algorithm? Because it was developed by Edgar Dijkstra. This is why it is called as Dijkstra's algorithm. What we'll do is we'll try to first have an overview of the steps followed in Dijkstra's algorithm, and then we'll dig deeper into each of the steps so that we stay clear on how to implement these steps. Okay. So first we'll have a basic overview. The point is you should have in mind of where we are heading to. Then it's easier to understand the exact implementation steps. Okay. So first thing is start with a source vertex. So let us say you have some graph like this. If this is your graph, you should have a source vertex. So this is your source vertex in this case. And you will have a lot of other vertices. Let us say A, B, C, D, E, etc. You should always start from this source vertex, because what is your aim? From this source vertex, you want to see what is the shortest path to each of these vertices. This is the final aim. So you should have a source vertex to start with. And then you should greedily pick the nearest unvisited node. How do you see which is the nearest? You have to find nearest unvisited node. How do you find the nearest node? This is based on edge weights. That is, let us say this edge is having a weight of 5 and this edge is having a weight of 6. In this case, SA is smaller, which means A is the nearest unvisited node right now. So what will you do? You'll pick the nearest unvisited node, and then you have to update the distances to all the neighboring nodes of A if a shorter path is found. What does this mean? First of all, you have to detect all the neighbors of A. So S you have already visited. Among the unvisited nodes, in this particular graph, C is the only neighbor of A. Neighbor means it should have a direct edge from A to that particular vertex. So let us say if there is one more edge like this, then D also becomes neighbor of A. So this is how you see the neighbors. And among the neighbors, what should you do? If you go through A, is there a shorter path than whatever you have already identified? This is what you have to see. For example, in this particular case, initially there is no direct edge from S to C, which means you will consider the total distance from S to C as infinity. So this is what we generally do in Dijkstra's algorithm. At the point when we are starting with this, we'll consider that the distance from source to all other vertices is infinity and the distance from source to itself is 0. After that, we'll start finding each of the neighboring vertices, and as soon as we are finding the neighboring vertices, we'll update the distance according to edge weights. This is what we do in Dijkstra's algorithm. So once you found C is the neighbor of A, you should see whether by going through A, are you finding a shorter path to C than what is already existing. If it is, then you should update it to the new path. This is what third step is. And what is the fourth step? Fourth step is to simply repeat these steps until all the nodes have been visited. So once you visit all the nodes, your Dijkstra's algorithm is complete. Now that you got a basic overview that we'll be starting with a source, we'll see for all the neighbors, whichever is the nearest neighbor, we'll pick it and then find all the neighbors of that nearest neighbor. Then we'll continue this process till the point we visit all the vertices. This is the overall process. Let us dive into and understand what exactly happens in this process and how are we able to identify the shortest path to all vertices. Okay. So to start with, you should understand how are you getting the input. Given that this is a graph, let us say G of VE, there are two ways to provide the input. One is as an adjacency list and the second method is as adjacency matrix. So this we discussed in detail in our graph lectures under data structures lecture series, that a graph can be represented by adjacency list or an adjacency matrix. In this particular lecture, we are considering that the input is adjacency list. In the next lecture, we'll be considering input as adjacency matrix, and then we'll solve for the same algorithm. Okay. So here we are considering as adjacency list. What is an adjacency list? You will have a list of all the vertices. So you can have this as an array, and then for each of the vertices corresponding to each of these vertices, you will have a list, let us say a linked list, which will have all the neighbors to this vertex. So let us say this vertex is having only one neighbor, then you will have only one node here. If this vertex is having 3 neighbors, then you will have 3 nodes here. So as a linked list corresponding to each node, you will show which are the neighboring vertices. So this is the adjacency list representation of a graph. So this particular lecture, we will be considering adjacency list representation, and then we will solve for Dijkstra's algorithm. We already know what is the input. We have an adjacency list. What is the next thing? You should know which is your source node. Your source node, let us say we call it as S. In this particular case, how should you start? The first step is you should have a distance array. Why should you have a distance array? This is your final output array. This will tell you what is the distance from source vertex to each of the vertices. So in this distance array, you will have one entry for each of the vertices. So initially, whatever be your source vertex, for that you will give an entry 0, because distance from the source vertex to itself is 0. And for all other vertices, you have to mark infinity. So infinite is what you are giving as distance to all other vertices. So as the algorithm progresses, you will change all these infinities and will be starting to put actual values. Okay. So initially you have a distance array. What is the second step? You already know which is the source, and what should you do here? Distance to source. This should be 0. So you already did it as 0 here. Next step is you should have a heap. This should be a min heap. Why should you have a min heap? Because in each step you need to find the nearest neighbor. So how do you find the nearest neighbor? This is by using min heap, not the nearest neighbor, whichever is the vertex having nearest distance from the source. So how do you find that? If you have a min heap, always the minimum element will be on top of the heap. So this is why you are using a min heap here. So what is the first step? You have to insert the entry 0s into min heap. So why are you adding 0s? The first entry 0, this shows the distance, and second one shows which vertex does it correspond to. So this particular entry says the distance from the source vertex to the source vertex is 0. So distance, every time we are considering only from the source, so that part is constant. This entry says to which vertex and what is the distance. Okay. So this entry is presently there in your min heap. You have one entry there. What should you do next? You should create an empty visited set. So next thing is a visited set. This should also be empty initially. Why should you have a visited set? Because this will tell you whether you have already visited a node or you have not visited a node. So initially you will have nil in all of these. That is, you have not visited any of the nodes right now. You are going to start the algorithm. Once you start the algorithm, you should iteratively go through these steps. What is the first step? These steps you have to follow iteratively. Okay. Till this point, it is one-time steps. And after this, these are to be followed iteratively. First step is you should extract the node U, which is the smallest distanced node from this min heap. So you have a min heap, and what is the advantage of your heap? Whichever is the node having smallest distance from the source, that will be on top. So you just have to extract the root of your min heap, and that will be the value with smallest distance from the source. So let us call it as U. Whatever you extracted from min heap, this particular vertex you are going to call as U. What are you going to do with U? First thing, you have to check whether U is already visited. Is U already visited? If it is visited, what should you do? You should just avoid this. You need not continue with this particular node. You can skip it. If it is not visited, then how do you know whether it is visited? There is an entry here in this visited array saying whether this particular node is already visited or not visited. So if it is already visited here, you can skip it from this step. If it is not visited, then you have to go to the next step. What should you do here? First thing, mark U is as visited. So once you mark U as visited, the next step is relax all the neighbors of U. So this is a very important step, that relax all the neighbors of U. First thing is, how do you identify neighbors? Neighbor means there should be an edge from U to V. Then V is a neighbor of U. So whenever you find a neighbor of U, how do you find this neighbor from? You have an adjacency list, and that adjacency list, first you should go to that particular entry which corresponds to U. What should you do then? You should go to the linked list corresponding to U. Each entry in this linked list, in your adjacency list, is a neighbor of U. So let us call each of them as V. What should you do with V? With V, you have to relax that edge. How do you relax? In order to relax, you have to see what is the distance till U, and then what is the weight of the edge UV. So if your distance till the point U plus the weight of edge UV, if this sum is lesser than whatever is the existing distance to V, then what should you do? In this case, you should update distance to V as distance to U, whatever be the distance to U, plus the weight of edge UV. How do you know distance to U? Because U is already visited. So you already finalized whatever is the distance to U. So that is why when you are seeing all the neighbors of U, we know that U is already visited, because of which distance to U is already known. And once you update the distance, what should you do? You should push. What should you push here? You should push this distance into your min heap. Distance of V and V. This is the entry that you should push into min heap, into your min heap. Why should you do this? Because now you know that you have a new entry, a new distance, which you found out to particular vertex V, which is smaller than whatever is the existing distance. So you should push this particular entry into your min heap, so that this is also included when you select the smallest node next time. Next thing is, you just have to repeat these steps. So these things I already told you, it is iterative. You have to keep it running in a loop. So repeat these steps until what should happen? Your min heap should become empty. So till the point your min heap is empty, you should keep continuing with these steps. What we will do is, let us try to understand this by looking into a graph. So we'll take a graph, and then we'll try to understand how exactly these steps are to be followed. So then it will be very clear for you. You'll understand it very clearly. We'll take an example graph. So let this be a graph. Let us say our graph looks like this. So this is our graph. We'll call a source vertex as A. Then you have B, you have C, then you have, let us say, D, E, and let there be an edge from D to E. Then we'll also have F here, and let us also have an edge from C to D. Okay, this is our graph. Next step is we have to give weight to the edges. So what should be the weight for edges? This, let us say the weight is 1, 2, 2, 4, 1, 4, and 1. And one more is remaining. Let us say this is 3. So this is our graph. We are going to find shortest path to all the vertices in this particular graph. What should you have? First thing is you should have a visited array. So what is your visited array? This is your visited array. What should be there in visited array? There should be an entry corresponding to each vertex. This is your visited array. You have A, B, C, D, E, and F. So you have one entry per vertex. And the other thing is you should have a distance array. So this is where you are going to keep track of distance to each of these vertices. To corresponding to each vertex, you have an entry in visited array as well as distance array. What is the next step? You have to start with the source vertex. What will you do? You know the distance to your source vertex is 0. So you should have a min heap. This is your min heap. In min heap, so what I'll do is, I'll simply write entries in min heap in ascending order, because min heap has a problem. The first particular entry is the smallest, but the remaining entries don't have any particular order. So it will be visually difficult to represent it. Even if I represent, it won't be so convincing for you. So what we will do is, we'll simply write in ascending order. So that will be more convincing. So let us say I'll write my min heap here. In my min heap, I have a single entry now, that is 0s. This means 0 is the distance to my source vertex. So what should I do as the first step? I already created distance array. My visited array is also created. I also inserted the entry 0s into my min heap. Next thing is, I should take the smallest node from min heap. So ideally, whichever is the smallest will be on top of the min heap. So I will extract the smallest entry. It is 0s is the smallest entry. So I already extracted. That means distance to my source vertex is 0. Once I take it, what is the first step? I have to see whether U is already visited or not. Is my source vertex already visited? A is my source vertex. So it should not be 0s, it should be 0a, because we named our source vertex as A here. Okay. So 0a. What about A? Is it already visited? It is not visited. What should I do? I should mark A as visited. So initially distance to source will be 0, but distance to all other vertices will be marked as infinity. Okay. So the next step is, I have to relax all the neighbors of source vertex. How do I relax? I have to see which are the neighbors. B is a neighbor. C is also a neighbor of A. Corresponding to each neighbor, I should update the distance. So what is the distance to B? Distance to B, presently it is infinity. The new distance is whatever is the distance to A, that is 0, plus what is the weight of edge AB. Weight of edge AB is 1. So my total distance to B now is 1. I know 1 is lesser than infinity. What should I do? See, I'm performing this step right now. I'm relaxing the edge. I'm seeing whether distance to U, here U is a source vertex A. So distance to A plus the weight of the edge AB, is that lesser than whatever is the existing distance to B. So our existing distance to B is infinity. So that is very large value. So whatever we found here, 0 plus 1, which is 1, is lesser than the existing value infinity in a distance vector. If it is lesser than whatever is in distance vector, what should you do? You should update d of v, that is distance to B, as whatever is the distance to A plus the weight of this particular edge. So once you update it, presently distance to A is 0, plus weight of edge is 1. So my distance to B will be updated to 1. Once I update it, what is the next step? I have to push D of V into my min heap. So whatever is the distance to V. In my min heap, I am pushing distance to B is 1 and the vertex is 1. So 1B is the entry I am pushing to my min heap. What is the next step? The next neighbor is C is the next neighbor to A. What will I do now? I'll see AC. So next neighbor is C. What will I do with C? I'll see whatever is the edge weight of edge AC. I will update distance to C as initially it is infinity. For now you can see in the distance vector, distance to C is infinity. I will see what is the new distance. New distance is distance to A, which is 0, plus whatever is the weight of edge AC. Weight of edge AC is 2. So my distance is 2. Is 2 lesser than infinity? Yes, it is. So I will update 2 here. So once I update 2, I am done with all the neighbors of A, which means I have visited A and I saw all the neighbors of A, and I'll update here to C. So in my min heap, I pushed C as well. At this point, I am done with A. What should I do now? From this point, I am going to iteratively follow the same steps. Okay. So let us do this slightly faster now. Iteratively, I'll be following the same steps. Okay. Whichever is the smallest, I have to pick from min heap. I'll pick 1B. So once I picked 1B, what will I do? I will see whichever is the neighbors of B. So keep in mind that whichever is a visited vertex, you don't have to visit it again. So A, you don't need to consider again. So whatever are the unvisited vertices. Among them, D is the neighbor of B. What should I do with D? Presently, whatever is the distance of D. Distance of D is infinity. So because it is infinity, I have to update it as whatever is the distance to B plus edge dB. So distance to B is, what is the distance to B? 1. So where did I get it from? This particular distance array. That plus the distance of dB, it is 4. So it is total 5. So what should I do? I should update the distance to D as 5 and I should put this particular entry in the min heap. So I'll have 5D in the min heap. I'm done with the neighbor D. Does B have any other neighbor? No, B is not having any more neighbors, which means I'm good for now. I'm done with the edge B. So B is also visited now. I have to mark B as visited. What is the next step? Take the next smallest one available in the min heap. So the smallest distance now available is to C. So I'll take 2C out of min heap. So once I take it out, I can remove it from here. So 5D is only remaining in min heap now. With 2C, what should I do? I should see whether C is already visited. C is not visited. So I can continue. I will first mark C as visited. Then I will see which all are the neighbors of C. Which are the neighbors of C here? You have E as a neighbor of C. Similarly, you have D as a neighbor of C. So what should you do with these? First, we'll do with D. For D, presently D is having distance of 5 in this array. So presently it is 5. Let us see if the distance 5 will decrease. What will you do? You will see whatever is the distance till C, D of C, plus whatever is the edge CD. So that is equal to, what is the distance to C? It is 2, plus what is the edge CD? It is also 2 here. So that is a total of 4, which is smaller than 5, which is the distance that we already found to D. What should you do? You should update the distance to D as 4 and add the entry 4D into the min heap. Okay. Once you do this, what is the other neighbor of C? Keep in mind, we are considering C right now. We are visiting C. So while we are visiting C, the other neighbor of C is E. What about E? E is presently having a distance of infinity. And how can you update it? The distance to C, that is 2, plus what is the distance of CE here? The edge CE is 4, which means the total distance to E becomes 6. So here I can update as 6. And what should I do? I should put 6e into the min heap. So once I put 6e, I'm done with all the neighbors of all the neighbors of C. So my visit of C is also complete. What is the next entry to be taken from the min heap? Smallest one is 4D. So I'll take 4D out of the min heap. Once I take 4D out, what happens? I have to see whether D is already visited, D is not visited, which means I should mark D as visited. And then what should I do? I should see whichever are the neighbors of D. So D has neighbors B, C, E and F. But among them, B and C are already visited according to the visited array. So we don't have to see B and C again. We'll only see E and F. What about E? E is presently having a distance of 6 in the distance array. So let us see what happens when you go through D. When you go through D, the distance to D is 4. So new distance to E is equal to distance to D, which is 4, plus the weight of edge DE, which is 1. So total is 5, which means your new distance to E is 5, which is lesser than 6. So if you go through D, you have a smaller path which you will update here. Update distance to E as 5. And what should you do? You should push the entry 5e into your min heap. You will push 5e into your min heap. After this, which is the other neighbor of D? Other neighbor of D is F, which is now having a distance of infinity. And how can you calculate distance to F? Distance to F is whatever is the distance to D, that is 4, plus what is the distance to F from D? DF is 1, which means it is 1. Total is 5, which means you can update the distance to F as 5. So presently we are visiting node D, okay? So we updated distance to F as 5 and you have to push the entry 5F into your min heap. So at this point you are done with D as well. What is the next entry to be taken from min heap? Next entry is 5D. So if you take 5D out, what is the first thing you have to look? You have to look whether it is already visited. So if you see the visited array, D is already visited, which means you don't need to visit it again. So you can skip it. What is the next entry available? It is 5E. 5E. Is E already visited? E is not visited. So you mark it as visited. And what will you do? You will see what is the new distance to E. So new distance to E is whatever, sorry, not E. You have to see for the neighbors of E. So presently, only F is the remaining neighbor of E, which is in unvisited list. So let us see only for F. So the distance to F is equal to whatever is the distance to E, that is 5, plus that of the edge EF. So EF is 3, which means its total is 8. Now if you compare, F is already having a distance of 5 and your new distance is 8, which means the old distance is better. You should not update. So F is having a distance which is 5, which is better. So you should not update the distance to F. You should leave it here. So you are done with this as well. After this, which is the next pick, 5E is already picked. Next is 6E. So if you pick 6E, what happens? If you pick 6E, E is already visited. So you don't have to visit it. You can skip this. You can skip this. Next entry is 5F. What about 5F? 5F is not visited. So you can mark F as visited now. But the point is, because all the other nodes are already visited, you don't have any of the neighbors of F to be considered here. So even if you consider, you won't have any improvement. So let us not do again. So F you can consider as visited and you're done now. So at this point, if you see the visited array, you can see the shortest possible distance to each of the nodes in your graph. And what if you want to track the path as well? That is, here we have the complete distance in the distance array. For example, you have D value as 4. 4 is the value for D. This means the shortest distance from the source A to the node D possible is 4. And how do you reach in order to get the shortest distance, you have to go AC first and after that do CD. In case you want to track this path as well, what should you do? In an array, you can just keep track of the path whenever we were going through this algorithm. So when we updated the path each time, you should just keep track of the path, then you can get path as well. So in this algorithm, we only kept track of distances. So we only have the value of distance right now. One thing more, that is, what is the time and space complexity for this algorithm? Let us go to this algorithm and see the time and space complexities. First thing, what is the time complexity? Coming to time complexity, let us start analyzing from the first step. First step is you have to create one particular distance array. So this should take total time complexity order of V. Considering there are V vertices and E edges in the graph, total of order of V. So generally we say time complexity in terms of the input count. That is, if you have n inputs, you will say order of n. But coming to graphs, because vertices and edges are equally important as a consideration for considering time complexity, we generally use V and E because so that we can clearly see whether it is in terms of vertices or in terms of edges. Okay. So order of V is the time complexity required for the first step. Second step, you are inserting single element to a min heap. It is order of 1. Third step, you are creating a visited array. It should be order of V, considering you have V vertices. Now comes the important step, the iterative step. In this, let us see how many times you are doing. First step is you are taking one particular neighbor. So this is simply extracting minimum element from the min heap. So what should it be? It should be order of log V. Okay. So one more thing here is, there is a question of whether it is log V or log E. Is it edges or vertices? So as of now, let us just assume that we are only entering those many entries as there are vertices. So for each vertex, we may have to put one entry into min heap. If that is the case, then it will be order of log V. What is the next step? You are having a check. So this should not take time. And then if U is already visited, you are skipping. The next step is, if it is not visited, what will you do? You will relax each edge. So this relax operation, how are you doing this? You are going to each of the vertices, that is whichever other neighbors, and you are relaxing. Given that you are having an adjacency list representation, you don't have to go to all the vertices in order to identify neighbors. Corresponding to each vertex, you directly get all the neighbors, which means whatever be the exact number of neighbors, that exact number is what you are going to do here. See, there is a reason why I am explaining this, because otherwise you will find out a wrong time complexity. Because if you see it like totally, you have to let us say do it order of V times corresponding to each vertex. You will relax corresponding to each vertex order of V time, and then you say that for each vertex you have to see for all the neighbors. Again, if you count this as order of V, you will think it is order of V into order of V, which is order of V square, which is wrong. Okay, so that is why I'm trying to explain it. That is, here, because you have adjacency list representation, for each of the vertex, you know exactly which are neighbors. So if you logically think about this, if you just forget about the mathematics like inside each loop these many times, instead, if you try to understand the total number of times it will be visited, counting all the entries into this loop, it will be at max the number of edges that you have. Why is it? Because let us say corresponding to each vertex you have entry here. How many entries can you have in total? Or if you take all these list node entries here, maximum number of entries is maximum number of edges, because each entry corresponds to an edge. What does each entry say? Each entry says corresponding to this vertex, there is a neighboring vertex called this. So that means there is an edge from this vertex to this vertex. So each of the node in this adjacency list will tell you it is an edge. So corresponding to each of the node in adjacency list, you will have to do this relax operation once, which means at max you have to do order of e times this relax operation. I am counting all the loops, okay? Totally, in this total iterative loop, if you count all the loop entries, in total you will have to order of e times execute relax operation. And not just relax operation will be order of e times. So in this relax operation, you have a push operation into min heap. And what is the time taken by push operation? Push operation will take order of log v time. But considering that we have order of e entrants, it would not be log v, it will be log e. Okay, it will be log e entries. So order of e times you are having log e operation, which means your total time complexity will be order of e log e. This is your total time complexity. One more thing. One more thing is it is not necessarily order of v. It can also be order of v in case number of vertices is larger than number of edges. If you have a graph in which, let us say, you have some isolated vertices as well. In this case, for example, in this graph, you have three vertices and only one edge. So if vertices count is larger, then you will have according to number of vertices. We are generally considering edge count is larger. That is why we said order of e. So to capture both those, instead of e, we will put e plus v. Okay, order of e plus v log e. The next question is, should it be log e or log v? So by the same reason, that is, if there are more vertices than the edges, then this can also be e plus v. So ideally you should put it e plus v. But wait, there is a catch. The catch is there is no point in saying log e plus v, because in worst case, what can be e? E in the worst case can be order of v square. That is, if you have v edges, what is the maximum v vertices? What is the maximum number of edges you can have in this graph? It is v square. If you have all the edges connected, in that case, worst case, you can have order of v square as the value of e. So in case it is the worst case, let us say it is order of v square, then this will be log v square, and log v square is 2 log v, which is order of log v only. So there is no point writing it as order of log e. You can always write as log v, because log e and log v both are of the same order. That is because e is worst case order of v square. So if you put v square here, it will become 2 log v, which is also order of log v. So there is no point in putting e or e plus v here. Log v will do, because of which time complexity of your Dijkstra's algorithm, considering adjacency list representation, is order of e plus v log v. This is the time complexity for Dijkstra's algorithm. One more thing, what is the space complexity for this algorithm? So the space is taken up, one is for the, so this is the time complexity. Space is taken up, one for the distance array, one for the visited array, and then for the min heap. In all these cases, you are having order of v as the space. And let us say if edges are more, in that case, in your min heap, you may need order of e. So again, we'll put space as order of v plus e. Okay, this is the space complexity. One last thing, given that it is order of v plus e, you may have a question, that is, instead of putting all the neighboring vertices here and pushing it into the min heap, why can't you actually do a decrease key operation on the min heap? You can also do this, right? If you do decrease key operation, at max you want to use only order of v space. So that is right, you can actually do a decrease key operation and you can do it in order of v space. The reason why we put it as pushing all the nodes vertices here is all the corresponding to each edge, we are doing the push because in implementations like, let us say, if you are using STL C++, in such cases, you will be using priority queue for this min heap implementation. So priority queue, let us say in C++ STL, doesn't support decrease key operations. So it is better that you don't use decrease key, instead just push. And whenever you are taking, you are anyway considering whether it is already visited or not. So it won't affect the algorithm. So that is why it is order of V plus E here. If you are using a direct decrease key operation, then you can consider as order of V as well. Okay. So this is about space and time complexities of Dijkstra's algorithm.